In this example, we'll calculate the pH of a weak acid, lactic acid, whose pKa value is 3.85. In order to calculate the pH of an acid, we need to be able to write out a reaction that this acid undergoes when it's in aqueous solution. It doesn't matter what lactate is, so long as it brings some H+ to solution. We can write down a generic formula for any weak acid as HA and show that it reaches an equilibrium with dissociated H+ cations and anions that we really don't care about in this problem. We need to set up an ice table for this equilibrium. To fill in our initial conditions, we know that the initial concentration of our acid is 0.250 molar, and before it starts to dissociate, there's 0 H+, 0 A- in solution. Therefore, this reaction progresses by losing some HA, gaining some H+, gaining some A- in stoichiometric equivalent amounts, so that by equilibrium, there's 0.250 minus X, and X amounts of each of these things. What we're after in this problem is the concentration of H+ at equilibrium. To calculate a pH, we need to know the negative log base 10 of the concentration of H+ from that equilibrium table. To help us get there, we should also write down a Ka expression for this acid. Ka is equal to the concentration of H+ at equilibrium times the concentration of A- divided by the concentration of HA. In this problem, that's equal to X times X divided by 0.250 minus X. Moreover, our Ka needs to be expressed as a number, not a pKa. pKa is equal to negative log base 10 of our Ka value. To solve for our Ka, we'll move a negative sign over and raise 10 to the power of both sides, so that when we have 3.85 equals negative log of Ka, we'll solve for Ka by taking 10 to the negative 3.85 power. That calculates to 1.41 times 10 to the minus 4. This Ka value can be plugged in to the expression we established up above in order to solve for X. 1.41 times 10 to the minus 4 is equal to X squared over 0.250 minus X. From this point, we could solve a quadratic equation, or we could take a simplifying assumption into consideration and check that assumption later to avoid solving the quadratic equation if possible. Our assumption that we'll make is that this X quantity is so small compared to the formal concentration or initial concentration of our weak acid that it's not appreciably different from 0.250. We'll assume that X is much, much less than the formal concentration of 0.25. What that means is that 0.25 minus X is effectively 0.25. We can rewrite the expression up above as 1.41 times 10 to the minus 4 is equal to X squared over 0.25 if we carry out that assumption. To solve this equation then, we just multiply both sides by 0.25, then take the square root of both sides. What this gives us is that X is equal to 0.00594. We need to check our assumption straight away. So over to the right, I'll make a check. To check our assumption, we calculate an alpha value. That's X over our starting concentration. In this case, it's 0.00594 divided by 0.250 multiplied by 100 to give us a percentage. In this case, that percentage works out to 2.4%. This is less than the typical threshold for cutoff of 5%, So long as we're below that 5% error mark, we're good. Our assumption works out, and we can use this calculation for X as our concentration of H plus at equilibrium, and we don't have to solve a quadratic equation. Now, one last step. We need a pH. The pH of this solution is the negative log of the concentration of H plus at equilibrium, which we now have as 0.00594 molar. Take the negative log base 10 of that quantity, and we end up with 2.23. This is the pH of our lactic acid solution.